So today is the first lecture, 2 lectures on Chapter 5 dealing with transient conduction. Hey, finally, we're not out of conduction, we're not to convection, we're not to thermal radiation, we're still in conduction, but we moved out of steady state. So now we have transient conduction. Now the first part of this chapter is pretty short, pretty brief, but it's important. It's very, very, very important. I would say that if you leave this class and you take the FE exam, there may be a question challenging to see if you know the concept of thermal capacitance and lumped capacitance approach to model transient conduction problems. You can generalize it. Just in the interest of time, I've always skipped this section. We just do conduction inside of a slab, a cylinder, or a sphere, and convection on the outside. That's good enough for our lumped capacitance model. But you could do thermal radiation. Tuck it in the back of your mind if you ever have just a purely thermal radiation problem. And yes, lumped capacitance may be justified. That's pretty slick stuff, but in the interest of time. Then down here, we have to pick it up and go through spatial effects through a slab, a cylinder, a sphere. And we have different ways of getting that exact solution. This is where it becomes very mathematical, but it's very powerful as well. So not only do we do it for plane wall, we do it for radial systems, and then that's where we'll end today. Next time we'll get into semi-infinite material, and that is very important as well. So let's just jump into it. So here's a first clicker question. So I've taken an image of something on this side of the page. Let's call this the left, and an image of something over here on the right. And can you just look at them and say, what is on the left and what's on the right? Are there resistors on the left, capacitors on the right, resistors on the left, resistors on the right, capacitors on the left, capacitors on the right, or what? Capacitors on the left and resistors on the right. What are they? Before I grade that, insert a new page. And just talk about this. I have this. What's that look like, in your opinion? Comes over to this. What's that look like, in your opinion? Goes to this. Or it also goes to this. All right, what would you call this thing over here? A battery. Voltage source. Perfect. So somehow, the way it looks like, this would be the high side, this would be the low side, or the positive and negative side. All right, this one's an easy one. What's this called? A switch. A switch, you can have it open or closed. So if you had it like this, what would the switch be doing? It would be closing the circuit. So, or the way I've shown it, it's opened. There's no current going through that switch. Okay. What is this device right here? Resistor. And what's this device? Capacitor. Professor, I don't remember anything. I don't want to remember anything. Well, then your job is a lot harder, okay? If you just want to forget everything about capacitors in the world. But your job is a lot easier if you can remember about capacitors. Let's play this game. Let's say I have this resistor. Let's say it's, 3 ohms. All right. Let's say the battery is a 9-volt battery. The first question I have for you is I'm going to close this switch. I'm going to let it sit there for a very long time. What is I in amperes flowing through the battery? Oh, I forgot to give you. What is my capacitor over here? How do we measure capacitors? In farads. Farads. I don't want to see a farad. I saw a farad. I'm still tremble when I see, no, you can't do that. All right, so this is going to be a capacitor, and it's going to be, let's say, 2 times 10 to the minus 6 farad. That's the capacitance. So we know our capacitance, 2 times 10 to the minus 6 farad. our 3 ohm with a 9 volt. The switch is closed. And after a long time, can you tell me what is the current I going through the battery in amperes? Go for it. All right, I'm going to go ahead and pick it up here, I guess. Let's stop this. What happens to the system after a long time? The switch is closed, and you wait a long time. What happens? The capacitor is full. It's fully charged. And so if the capacitor is fully charged, isn't it as if the capacitor is not even in the circuit anymore? Just like that. All right, so now it's simple, isn't it? Oh, you put the capacitor in, you fooled me, you tricked me. No. So isn't it just Ohm's law at this point? So you have the current is equal to the voltage difference, which is the 9 volts provided by the battery, divided by the ohms, the resistor. And is it, hey professor, is a volt divided by an ohm an amp? Is it 3 amps? Let's grade it. So 100% of the 30 people, is that right? That's pretty good. I'm amazed. That's good. So now the next part, that's a lot better than I've seen in the past, is I take the switch after it's been closed for a long time and I open it. I open the switch. Now what happens to the current that used to be going through the resistor? At the instant that I opened the switch, it was 3 amps. At picosecond afterward, what is the current going through that resistor? How does it change from 3 amps? Does it stay the same? Answer A. Abruptly go up, answer B, or go down, answer C, or go to 0, answer D. So what does the current going through that resistor do immediately after I break and open the switch? All right, so there's your A, B, C, D, and we'll switch it to multiple choice. Go. All right, well, as soon as the current just doesn't turn off, the current still stays 3 amps. But how much is going through this open switch? 0. So how does you still get 3 amps? It's coming from the capacitor. The capacitor now was sitting there happy. It was fully charged. Now it's starting to discharge. That's right. And so it stays the same. The best answer is answer A. It stays 3 amps. Now, let's say I wait a long time after the switch has been opened. And now, what is the current through the resistor? We can just do this verbally. Sounds like you got the best grasp of it. Tell me, what does the current do through the resistor? I open the switch. It stays at 3 amps, but then it's going to change after a long time, right? What's it going to do? It's going to go to 0. It's going to decay. And why is it going to go to 0? It's going in this loop right here. It's discharging the capacitor. So what is the voltage? You could do it a number of ways. You could say, what's the current through the resistor as a function of time? What's the voltage across the capacitor as a function of time? What's the voltage across the resistor as a function of time? Or, the current through the capacitor as a function of time. And if you said that this is time right here, and 0 is when the switch gets opened. You break it and you throw it open. We said it was up here like at 3 amps. You could call that that I initial, I sub I or I0. What does it do? It's kind of just a boring function. What is the most boring function in engineering and science? The exponential function, isn't it? And so doesn't the current through the resistor as a function of time? Isn't it the initial times e to the minus, and now you need to help me up here. I know that time is up there, e to the minus t for time, but something else, another player or something's up there, a constant. What is that? What do we call that? I'll put this over here. Isn't it RC? RC, the product of the resistance value in ohms and the capacitor's value in farad. And so for this problem right here, oops, I lost my page there. For this problem right here, I have, sometimes they'll put tau as the time constant, and it's equal to RC, and it's equal to, how many ohms did I say? We had 3 ohms times 2 times 10 to the minus 6 farads. What is that in seconds? 6 times 10 to the minus 6 seconds. That's the time constant. Isn't it? Isn't it? So tau is 6 times 10 to the minus. That's our time constant. That's how this thing decays. How long will I have to wait for this thing to essentially be out to 0? And if you wait 3 time constants, 1, 2, 3 tau, you're down to 5%. If you wait till 5 time constants, 4, 5 tau, you're down to really small. Just put in your calculator e to the minus 5. What do you get? 0.0067. It's less than 1%. Less than 1%. So there's a few things we should know about the exponential function. 3 time constants get you down to 5%, and then 95% of the action's over, and then if you go to 5 time constants. Now, that's all a good review. Oh, I forgot. We never did grade this, did we? What are these? They're all capacitors. Capacitors on the left, capacitors on the right. So now we want to talk about a thermal capacitance. So the analogy is you take an object. The temperature of the object is going to change as a function of time. And we're not interested in the temperature within the object. It can conduct heat within the object pretty easily and get it to the boundary of the object by which it then is convected off to cool it. So we would start with some initial temperature, and if we put it into this fluid bath over here, dunk it into a colder fluid bath, that is some T infinity, eventually it's going to get all the way down to the fluid temperature, T infinity. A large bath, if you put a small object in, it's not going to greatly increase the temperature of the bath. So we're going to assume it's huge, so it stays T infinity. Okay, so what happens is it goes like this. Hey, you solved that problem when you did the electric circuits problem and the RC. That's all it is. So you just have to do the parallels with the analogy. So when you dunk this object in there, you start to have convection, H, off the surface of this object into the fluid. So we'll say the rate of change of the internal energy with respect to time is equal to the rate at which it's going off of the object. I'm going to put Q, and I'm going to put negative by convection. Hey, where'd that equation come from? First law of thermodynamics. I just have a system like this. I have a system like this, and I'm convecting off of it. Okay, so what is my model for the internal energy? Do I know the mass of the system? Do I know the specific heat of the system? And do I know the temperature? dt, d time, right? Isn't that the way the internal energy is changing with time? And if I'm adding heat, that's going to be positive going up. If I'm removing heat, it's going to be negative going down. So that's why we put a negative. Then we have the HA. Then we have T, the object minus T infinity. The assumption for the thermal capacitance, we have only one temperature. The quantum that is a function of time, and it's the temperature of the object. The temperature in the middle of the object is the same as the temperature at the edge of the object, or the surface of the object. Only one temperature for the temperature of the object, and that's here and here in that equation. We have a First order differential equation, we have initial condition that t at time equal to 0 is equal to either t init or ti or to or something like that. Let's put t subscript I. Well-posed mathematical problem. Can you solve it? Sure. So what we'll do is we'll introduce a temperature difference. We'll call it theta. T minus T infinity. Isn't theta this temperature difference? And isn't theta going to go to 0 now? Instead of T go to T infinity, we're going to have theta starts at some initial value and then goes off to 0. Okay, so the differential equation is rate of change of theta with respect to time is equal to minus HA over MC theta. All right. You then put theta initial is equal to, well, theta at time equal to 0. At 0 is equal to theta initial. All right. Now we solve it. So you get that the solution theta is equal to theta initial e to the minus. And then what do we have here? We have HA divided by MC and T. Or you could put it like this, is equal to theta initial minus T divided by MC over HA. So this MC over HA, I'll rearrange it a little bit. The mass is the density times the volume. The specific heat, we have the convection, and we have this area. All right, 1 over HA times rho VC. This is the resistance, thermal resistance, 1 over HA. That's our convective thermal resistance. And so our thermal capacitance must be rho CV. It's kind of almost unexcited, you know, just like, whoa, I understand what happens with electrical. I have the analogy over here with the thermal. It's pretty straightforward. So the thermal capacitance is just rho VC or MC, mass times specific heat. And the thermal resistance, 1 over HA. That's the solution. Okay, here's the equation with the whole time and then the HA divided by rho VC with the minus sign. Exponential, you could get rid of put the theta divided by theta initial. So now what does it start at? It starts at 1 and it goes down to 0. The exponential function. All right. The next one that I want to talk about is the validity of the lumped capacitance method. So I have this object, and I have some temperature and the temperature of the surface. If it's being cooled, if the fluid over here is colder, so T infinity is less than the temperature of the object, then what do you think the difference is between the surface and where would be the highest temperature? The maximum temperature would be somewhere in the center. Temperature in the center, right? And so the whole thing becomes, is the temperature of the center about the same as the temperature of the surface? Okay. Well, what you do is you think of having 3 nodes with 2 resistors. And you say, well, I know what the convective resistance is to go from the surface out into the fluid. Isn't that 1 over HA? Well, what would be the resistance to go from, let's say, the centermost location of the object to the surface of the object? Well, it's going to be some sort of the resistance will be some sort of length scale, L over K A. Get rid of that right there. So L over Ka, that would be some resistance. So if somebody said, what would be, if this is for at any instant in time, this would be the same I. So you can say the I in the conduction is equal to the I for the convection. What's the flow? So here in heat transfer, It would be the Q for the flow. Okay. What is our equation for the conduction? The flow is equal to the temperature difference, temperature of the center minus temperature of the surface, divided by the resistance, or if you don't even want to divide by, you put the Ka over L. And how about for the convection? It would be the temperature of the surface minus the temperature of the fluid far away. What would this be? The HA, or 1 over HA if you're dividing by the resistance. All right, so this temperature difference, Tc minus Ts, if I divide by Ts minus T infinity, if this is really, really small, much, much less than 1, then that really is confirming when I'm assuming when I have the lumped capacitance. It would be like the centermost temperature versus the surface temperature are about the same compared to the difference between the fluid temperature and the surface temperature. Okay, well, what is this ratio? This ratio is HA divided by Ka times L. Now, before we cancel the A's, what is A times L? Some sort of volume. And so they'll have H divided by K, but they'll have LC. So this is some characteristic length that L sub C is equal to something, depending on if it's a slab or a cylinder or a sphere. And that's on the next slide where I summarize those. But what you'll do is you'll calculate what they have called the Biot number. The Biot number being some H, characteristic length, divided by C. And if the Biot number is much, much less than 1, that means that this temperature difference ratio is much, much less than 1, then the temperature difference of conduction inside the solid is negligible compared to the temperature difference of convection getting it from the surface into the fluid. It's isothermal. It's uniform temperature in the solid that only one temperature quantifies the solid temperature, and it's only a function of time. All right, so there is our thing. This always brings up a good question. It's like, we just talked about the exponential. When's the action done when you have this decaying exponential? 5 time constants. All right, here, what's much, much less than 1? And that's a judgment call. And so if somebody said 2, is 2 much, much less than 1? What would you say? No, it's not. All right. How about 0.2, 20%? Is that much, much less than 100%? No. Most people would say no. How about 0.02? Yeah. Yeah, I mean, just say 2 pennies compared to $2, right? I mean, you're just trying to put some common sense on this. 2%. It's, yes, 0.002, definitely. So somewhere in between 0.2 and 0.02 is the cut, and most people would say about 0.15, somewhere in there. 15%. You're getting sometimes your tolerance, if $1 billion is on the line. Well, okay, let's really go out there. Sometimes, look, I got a control strategy and I need an estimate of the worst case. Well, 15% close enough. Let's go. Let's not waste our time or spend more effort here. So somewhere around the breaking point, 10%, 15%, somewhere around there. All right? It doesn't have to be down less than 1%. Okay. So what was our characteristic length? It was our volume to area ratio. So if we have a slab, the book often puts the x-axis starting 0 goes to L to minus L. All right? So our characteristic length is our volume. So if I think about our volume, it's going to be the face area times 2L. So our volume times 2L gives us, our area times 2L gives us our volume. You divide by our area, the areas cancel. And so the characteristic length, L sub C, Oh, I forgot. I have an area on the right and an area on the left. So the two areas, so it's just the half thickness of something, a slab, which is convectively cooled on both faces. Okay. Okay. How about for a cylinder? Well, we have a cylinder. It's very, very long. So this L is much, much greater than the radius. And this will be the radius, and we'll put R naught or cap R. Cap R or cap R naught is the outer radius of that cylinder. So now what is our characteristic length? It's our volume divided by area. Volume. Okay, what is my volume? Is it pi R squared times L? Does that look good for a volume? Sure. And then what's my area for the convection? The convection is happening over this surface out here. I'm neglecting the two ends because it's very, very long. It's just going to be 2 pi RL. So we cancel the pi's, one of the r's, the length, and so the characteristic length is the radius divided by 2, or R naught divided by 2. It's the outer radius divided by 2. Okay, how about for a sphere? Well, the sphere has radius R, cap R. What is the characteristic length? It's the volume divided by the area. What's my volume of a sphere in terms of the radius of the sphere? 4/3 pi R cubed. What's our surface area? 4 pi R squared. Cancel the pi's, cancel the R squareds, cancel the 4's, and what are we left with? Characteristic length for a sphere is R divided by 3. Those are my characteristics lengths. How do I use it? We use it in the Biot number, H L sub C divided by K. If it's much, much less than 1, then it justifies the use of the lumped capacitance. When we have a transient analysis of something like that, we look to see if the lump capacitance can be used because it's very simple to use.
All right, and all of these are assuming that we are cooling it from both sides.
Well, yeah, all the way around on the cylinder, both sides of the slab, and exactly the sphere as well, the outside surface of the sphere. Mm-hmm. So the Biot number, that's how you spell it, is in a table in our textbook. Here's the Biot number, the name, and then BI. Is it a B subscript I, or is it a BI? What's the I? Subscripted or not? It's 2 letters. The second one is not subscripted. It's just BI. All right, so let's take a look. Here's the definition. Does that make sense? HL divided by K of the solid. Why do they put a subscript on there? Because you're going to be convecting it into a fluid. You have the thermal conductivity of the fluid as well as the thermal conductivity of the solid. Some students might pick the thermal conductivity of fluid. Would they be correct? No. It's the thermal conductivity of the solid right there in the use of the Biot number. Okay? And it's a ratio of internal thermal resistance of a solid to the boundary. So internal to the boundary divided by the thermal resistance off of the surface, off of the boundary into the fluid. That's what we just talked about. There's another number we're going to use in this. So while we're in this table, let's go ahead and take a look at it. It's down here. Fourier. Hey, I've heard that name before. Have you heard the name Fourier before? Of course, in your math classes, yeah. And so here is a Fourier number, same individual, all that work in math. Is the O subscripted or not? Not subscripted, it's just 2 letters, FO, Fourier number. Now, here's the definition, alpha T divided by L squared. What is alpha? Alpha. Alpha is K divided by rho C. It was introduced like at chapter 2 or something. It's a thermal diffusivity. Thermal diffusivity. It has units of meters squared per second SI units. thermal diffusivity. So here we go. Alpha times T divided by L squared. Is that going to be dimensionless? Check your units. So we have the meter squared per second, time, seconds, length, meters, but we square it. The meter squareds go, the seconds go. Fourier number is dimensionless. It's simply a dimensionless time. The book sometimes will use a T asterisk for dimensionless time, or they'll use this asterisk as a dimensionless property. Okay, like they'll use theta asterisk. Theta asterisk is theta divided by theta initial. It's a temperature difference divided by a temperature difference, so it's a dimensionless temperature difference. They'll use x asterisk, which is the location x divided by L. Dimensionless location. Here, this dimensionless time, they give a special name in honor of Fourier. So they call it the Fourier's number, just like the dimensionless Reynolds number. Okay. There's other ones that I just copied, but the Biot number we're familiar with now, and the Fourier number will become more familiar with when we do the spatial effects. So the general lumped capacitance. Professor, radiation, it's pretty slick, it's pretty neat, but I'm not going to have an exam problem on it nor homework problems on it, so guess what? Most students would just skip this whole section. But just remember there's more out to the generalized lumped capacitance approach than what we cover in this class. All right. Solve a problem. So we have a solid 3 centimeter diameter. Right away, be careful. Is this radius 3 centimeter? No, the radius is 1.5 centimeters. You'll get off by a factor of 2 by mixing diameters and radiuses. Okay. It's a sphere. Good. It's made of copper. When you think copper, what do you think? High thermal conductivity. Down here they give you the thermal conductivity. It's nearly 400. It's heated in a furnace for a long time, and the temperature throughout the sphere is 80 degrees C. It's coming out hot. All right. It's abruptly removed from the surface and exposed to 20 degrees C air at that convection coefficient. Here are the properties of copper, this density, the specific heat. How long will it take for the center of the copper to be cooled to a temperature of 50 degrees C? First step in a problem like this, see if you can use lumped capacitance. Because does it matter if it's the center or the surface of the copper if lumped capacitance is justified? It's the temperature anywhere in the copper. It would be one temperature as a function of time. Okay, so we check the Biot number, which is the H. I'm going to put the radius divided by 3 because that's a characteristic length for a sphere. Divided by K. So we put in our value of H, 75 watts per meter squared degree C. The radius, which is 0.015 meter divided by 3. The radius divided by 3. Did I do the meter correct on that? The centimeters to meter? Good. And then the thermal conductivity, 388 watts per meter degree C. Check your units. Watts go, watts go. Meter squared, meters squared. There you go. All right. Somebody want to run this number for me? What do we get for a Biot number? 9.66 times 10 to the negative 4. How do you like that? And so much less than, we love it when it's so clearly, it's not near that, transition. This is, 0.15, 0.12, 0.8, 0.08 or something. Is that much less than 1? Well, this one is definitely much less than 1. Lump capacitance is justified. So how long does it take for the center of the copper sphere to be cooled to 50? So maybe you'd like this equation. Theta is equal to theta initial e to the minus T divided by tau. All right, give me the time constant. What is my time constant for this problem? It's our resistance, which is 1 over HA, times our capacitance, which is mass times specific heat, or rho V C. All right. Let's just put in some numbers for our 8930 kilograms per meter cubed. The volume, 4/3 pi, radius 0.015 meter cubed. 4/3 pi r cubed. Is that correct? Good. The specific heat, 385 joules per kilogram degrees C. Divide by the convection coefficient, 75 watts per meter squared degrees C. And then the area. What is the area? 4 pi 0.015 meters squared. You could have simplified the volume to area ratio is just R/3. Could have done that too. Okay. So we find that our time constant comes in around 229.2 seconds. Tau, maybe I should put tau. Tau is equal to. All right. Now, our theta that we want to get to is, excuse me. We want to get to 50. The T infinity is 20, so that's our theta at the end. That's how long do we have to wait before theta is 50 minus 20. It starts off 80 minus 20, that's theta initial. We have e to the minus, the unknown time that we're trying to solve for, divided by the time constant, 229.2 seconds. I think you can solve that, right? Just bring it over, exponentiate both sides, don't forget the negative sign. And so t will be 229.2 seconds with the minus sign. Natural log of 50 minus 20 divided by 80 minus 20. And so the time comes in at around 160 seconds. Did that look okay? You do a problem like that? Plenty of homework problems. And if I don't have one on the next test, I'll have it on the final test. The probability of having a lumped capacitance problem on an exam in this class is nearly 100%. It's just that important.
When you ask for the time constant, you want it in seconds or seconds asterisk?
Your call. I mean, I've seen problems where they report the answer in minutes or hours versus seconds, but the time constant will be measured in time. Tau will be in some sort of time right here. And it's a helpful step, intermediate step.
So the Biot number was just to verify that.
Ready to press on? Okay. What are the units of the time constant? Okay. So I mean, it is simply just a time. That's all it is. And it's a fixed amount of time. So tau would be something like, I don't know, 93.2 seconds. Or tau would be 1.68 hours, whatever. It's a time constant. And so it has dimensions of. Seconds is best, right? It's dimensions of time. It's you have e to the minus t divided by tau. And when you do that, this needs to be dimensionless, e to the dimensionless something. Time would be in seconds, tau would be in seconds, great. Or minutes over minutes, or hours over hours, whatever. I'm going to skip those. Let's see if I like this one. Probably not. Do you want to do this one or not? Okay, we'll do it. The initial temperature difference, theta initial, is 50 degrees C. The time constant, tau, is 20 seconds. What is the temperature difference after time of 20 seconds? After a time period has elapsed of 20 seconds, what is that temperature difference? theta. E to the minus 20 over 20. Hey, that's e to the minus 1. We can sometimes remember what e to the minus 1 is. Roughly, if you just had to throw something out, you're down 2/3 of the actions over. I know it's like 0.37, isn't that it right? 0.37 something? 63% of the actions over, and 37% is remaining to happen. So you've gone a long way in just one time constant. And so take the 0.37, multiply that by the 50, and you get about 18 for the correct answer. Very good. Wow, I'm impressed. Very nice. All right. What is the main assumption underlying the lumped capacitance method? Temperature is constant in the solid object. Temperature is uniform in the solid object. Temperature is a function of location in the solid object. Temperature is a function of time and location in the solid object, or that the Biot number times the Fourier number is much, much less than 1. All right, I stop. And we show the results. Okay, this one's a little tricky. If it's constant in the solid object versus uniform in the solid object, uniform means it's the same temperature everywhere, but if it's constant, that means it's not changing at all. But ours is changing with respect to time. So the best answer is B, although a temptingly wrong answer is A. And then this is just some sort of bogus. We haven't talked about the Fourier number yet other than introduce what it is. So now what I'd like to do is toggle a little bit. We're still in this chapter on transient conduction, but we need to consider spatial effects. So now we would like to only solve temperature as a function of time. But if lumped capacitance is not justified, we have to consider temperature as a function of time and location. We're going to do it in the slab, and then later you can do it in a cube, or where you have temperature as a function of x, y, and z, as well as time. But believe me, you want to just start off with the slab first, or temperature is radius as well as time for a cylinder or a sphere. So before you jump into multi-space dimensions, handle just one space dimension with time. That's hard enough. Okay, so we'll deal with a lot of the plane wall, just focusing on the plane wall right here. And then later we'll do the radial systems with the convection, cylinder or sphere. Yes, exact solutions. This is the section that's very mathematical. But before we get into mathematical, let's just talk. Here's a slab. Where's the x coordinate system? The center line. It goes plus L minus L, so the slab thickness is 2L. You're convectively cooled on both faces of the slab, and we're interested in the temperature as a function of time as well as location x. X runs between minus L and plus L. Right? Okay. So now, what did they show right here on this slide? Just a 2D projection. And what they did was they have on the x running this way, x goes between 0, L, and then back to minus L. What do they do in the y? Well, they'll plot temperature. We'll recycle T. The height is showing the temperature. So what do they do here? They have a red line showing the temperature everywhere at all x of interest when time is equal to 0. And they put T subscript I. What's that mean? It's initially uniform temperature. And it's hot, isn't it? Can you see how high a temperature it is? Now, after a long time, it looks like the whole profile is going to be like this. So on the y-axis, if this is an estimate, that height is T initial, This one down here is T infinity. That's the fluid temperature. After a very, very long time, it's a very boring profile. It's all just in the slab. It's just boom. Now, what they're doing too is they're trying to show you the temperature profile in the fluid adjacent to the slab, but they didn't really need to do that. Don't let that confuse you. Just focus on the temperature between negative L and plus L. All right. What about right here? Where is it hottest? After some time, it's hottest right in the middle, like you would expect. But what about the surface temperature? Doesn't it look pretty close to the center line temperature? Sure. How about at this time? Maybe this was 1 second later. Maybe this is 3 seconds later or 3 minutes later, whatever the time scale is. Now, what is the center line temperature? And then this is the two surface temperatures. Aren't they about the same at that later time? And then we come down here. Center line, surface, aren't they all about the same? What are they showing us? That basically, if I check the Biot number for this problem, it would be not less than 0, much less than 1. It's small. It's a small Biot number. It's basically our concept of uniform temperature in our slab. Okay, you understand that plot? Now we can up our game a little bit. Okay, I answered that question. Do you want to try and get some easy clicker questions? Okay, I'm not even going to read it to you. You figure out that one. It's basically that it's the initial temperature. That's what we're saying. At all x and at time 0, what's the initial temperature? Okay. What is the T at all x? No, x equal to 0 at the center at the large time. What does this mean that time much, much greater than 1? It's a long time. After a long time, doesn't the temperature profile go flat? And isn't it everywhere in fluid temperature? Yeah, so the best answer is that it's everywhere at T infinity, the fluid temperature. Okay. Now, what do? Is we have this case A we just talked about, right? But you could think something that looks like case B or some thermal response that looks like case C. This is straight out of the textbook, just trying to talk through one of the figures. And so what's the difference between this case and that case and that case? Well, just take a look at, let's say this is the time of 1 second. Maybe that one's the time of 1 second, and this is the time of 1 second, right? If I compare the center temperature with the surface temperature at 1 second, the center temperature versus the surface temperature at 1 second, the center temperature versus the surface at 1 second. Can you see what's happening? We're getting a more severe temperature gradient inside my solid. It's not justified to be lumped capacitance anymore. There'll be a significant difference between the center line temperature, come on, I can do that, center line, versus the surface temperature. Okay. If you take a look at all of these three cases, which case has the largest H, assuming the thickness L is the same, the thermal conductivity is the same, the thermal capacity is the same? All you're going to do is only change H, the convection coefficient. So yeah, the largest H is this case C, where it's really cooling. When you have a large H, isn't it cooling the surface? Rapidly cooling the surface. And that makes it much difference in the internal temperature difference. Okay, check the Biot number. Is it H L sub C over K? If H goes up, what does the Biot number do? Goes up. It's hard to be small. So it's going to become, you're not justified to use a lumped capacitance. Typically when you have very large H, or what about K? I could do the same game. If I had copper, copper is a good conductor. Maybe I make it a stainless steel. It's a lot lower thermal conductivity. So this goes down, the Biot number goes up, and not justified to use lumped capacitance. Okay, so there's more of those. So for this problem, you have to write a differential equation to be used to solve for the temperature as a function of this location x and time. You need, for that differential equation, you need boundary conditions. How many? 1 or 2, as well as initial conditions. How many? 1 or 2. So, well-posed mathematical problem. What's the differential equation? And then, what are the boundary conditions and what is the initial condition? Or conditions. I should put. So, isn't our differential equation the heat diffusion equation? Not Fourier's law, but our energy balance equation. So we're going to come in with, I don't know if you want to put it to second derivative of temperature with respect to space. You could put the K on the outside, you could put a Q dot here equal to rho C partial of T with respect to time. Professor, we don't have any heat generation. Good, knock it out. There's your differential equation. Second order. What's this? Modeling conduction. What's this? Modeling the accumulation depletion in change in internal energy reflected in a change in the temperature. If it's hotter, it has more internal energy. All right. Somebody says, I like it when it's the partial second derivative of the with respect to space, and then you have 1 over alpha rate of change of temperature with respect to time. What's alpha? Alpha is our thermal diffusivity, our K divided by rho C, just a property. That's a good way of writing it, a little more compact. Well, it has 2 derivatives for the space dimension. How many boundary conditions do we need? 2. Where do you want to pick them up? Pick them up at x equal to 0 and x equal to L. All right, so at x equal to 0, what do I have? Something special about all of them. They're flat. That means the temperature derivative, the derivative of the temperature, the rate of change of temperature with respect to x at x equal to 0 is 0. It's symmetry. It's as if it's quote-unquote insulated. A couple of different ways of looking at that boundary condition. Okay. And then at x equal to L, what do we have? Do a very thin little control volume right there at the boundary. What do we have coming in on the left? It has to match what goes out on the right. You could do it on a per unit area basis. And so what we have is we'll have Q double prime conduction equal to Q double prime convection. That's for our boundary condition at x equal to L. What do we have for a model of conduction? Minus K. The derivative, I'm going to leave it still a partial derivative. I need to scoot down just a little bit. Minus K, partial of T with respect to x at x equal to L. Where did that come from? My head is spinning. I don't understand. Where did that come from? Fourier's law. That's all that is. And then we have H, then we'll have T at x equal to L minus T infinity. That's our second boundary condition number 2. Yeah, you can change it up some more, but maybe I'll write it over here. The rate of change of temperature with respect to x at x equal to L is equal to H divided by K. T at L minus T infinity. Leave it right there. Thank you very much. Need that negative. And then what about our initial condition? Well, look at right up here. The temperature at all location at time equal to 0 is equal to the initial temperature. One initial condition, 2 boundary conditions, a second order partial differential equation. You can solve it. You are well equipped. That's all you did for a whole semester, solve PDEs. What is the boundary condition at x equal to 0? Multiple choice, 30 seconds. And we'll show the results. Yeah, it's C. C, this one right here. It's flat on the temperature profile. The derivative with respect to space of the temperature profile at x equal to 0 is 0. All right, very good. Next one. 30 seconds. What is the boundary condition at x equal to plus L? This one right there. And we'll just show it. D is the correct answer. Again, you have what is this statement? How did I get this statement? What's this equal to? That's the Q double prime conduction for a little bitty control volume, thin control volume, just on the right side, or that's the left side, sorry, the left side of that control volume. And this is the convection, Q double prime convection, just a little bit on the left, or the right. Now I got the right mixed up and left mixed up. The right. All right? Okay. How do you solve it? Well, I'm just going to summarize the solution. So this is my differential equation. I introduce theta with theta initial. I'll even have theta asterisk or theta hat. It's just a dimensionless temperature difference. Got it? We introduce x asterisk or x hat, as well as the Fourier number, which is some t asterisk or t hat. So we have dimensionless time, dimensionless space, dimensionless temperature difference. Now you've transformed that to this. Where'd the alpha go? Well, it's embedded in the Fourier number, or that dimensionless temperature. Okay, that's pretty straightforward. You still use these definitions to transform, what's this? My initial condition. Then I transform the boundary condition at x equal to 0 and transform the boundary condition at x equal to L. Hey, what popped up in this equation? A Biot number. What's a Biot number defined as? HL divided by K. Now, you do a 3 dots. Dot, dot, dot. Huh? Even if I repeated all that, it wouldn't be worth it. I'm putting you to sleep already. Dot, dot, dot means a lot of work. And you'll get a solution. It's a summation. It has some coefficients. Here's an equation for the coefficient. Has some cosine for spatial dimension. Has some exponential for temporal, how it changes with time. It's actually not that hard. But in the interest of time, I don't have time to go back. You get a transcendental equation that I need these zetas. And the zeta 1, zeta 2, zeta 3, zeta 4. So this is a transcendental equation. It has a coefficient in it, the Biot number. And you get multiple roots to this. The book does a good job in this chapter summarizing that, but you really need another reference book like Kreisig or Green or some other ones. First 4 roots are in Appendix B. I think I show that on the next slide. And what's interesting is when the Fourier number is greater than about 0.2, meaning you've marched enough out in time. The Fourier's number is dimensionless time. What it is the higher order terms can all be thrown away. They're negligible. And the first term survives. Is the only one that really is needed. And so this series solution, that's what, you show your friends to impress them. Oh yeah, we're mechanical engineering majors. We have to know all the math and all the physics and be able to be creative and design things and blah, blah, blah. I'm so good. Yeah, let me show you some of the equations we use on a daily basis. Here's my PDE. Yeah, just whipped out the solution yesterday. And look at this, series summations. But anyway, it all boils down to just the first term when the Fourier number is greater than about 0.2. Now, you think on a time-limited exam, the professor is going to give you, something where you could have to sum at least even the first 4 terms on that series solution? So if you're going to use this equation on a time-limited exam, it's like 99.9% of the time, the Fourier number is beyond 0.2, one term. So, and then a lot of times they're interested in the maximum temperature. Where's the maximum temperature in this? Is it at the surface or in the center line? The center line. So often it boils down to something really simple like this. But this captures the difference between the temperature at the surface as well as the center line. Let's go on. Here is that appendix, and they have the 1, 2, 3, 4. What's it a function of? Biot number. Look at the transcendental equation. Zeta, tangent of zeta is equal to the Biot number. If I change the Biot number, it changes with the roots. So what you have to do is typically look up the Biot number. Oh, I have a Biot number of 0.4. Well, there's zeta 1, there's zeta 2, etc. You may have a homework problem where you need to do 4-term summation. But on an exam, pretty low probability, very low. Now, you can do the same thing, not just for the slab, you could do it for the sphere and the cylinder. So this table is one of the most important tables in the chapter 5. It gives us the first zeta. Hey, what are the units of that zeta? Rad. I never heard of rad. What is rad? It's a radian. Radian. All right, and then they give you the coefficient C1. So this is for the plane wall, this is for the infinite cylinder, this is for the sphere. So as a function of Biot number, let's say the Biot number is 0.07. I'm going to need this zeta 1 and this C1, and I can use that first term if the Fourier number is greater than 0.2. Likewise, if I have a cylinder, infinitely long cylinder, I would grab those if my Biot number was 0.07, likewise. So you just have to find it now. Every now and then you have to interpolate. The Biot number is in between. Okay, well, just do your linear interpolation. Sometimes very important statements which have cost points on many exams for students are at the bottom of the table. Okay, so this bottom of the table, we go down here to Biot number of infinity, but what's this line right here? What is this? Biot number for a plane wall. This is the Biot number for an infinite cylinder or sphere. See the figure 5 point. Read this multiple times. This is very important because what do they say is the Biot number used right here? That's where that subscript A is, coming down here for the footnote. They say for a cylinder, it's H R naught divided by K. Professor, I thought we were going to use a characteristic length, and for characteristic length, it's the radius divided by 2 of my cylinder. That's to check the lumped capacitance. If you can't use the lumped capacitance, when you go to the analytic solution, the Biot number is different. It's not R over 2, it's simply R. Do you see the problem? It's like, hold it, why didn't they just stick with one definition of the Biot number? Don't ask me. I'm just telling you that's the facts. And so the Biot number in this table for a sphere is H R naught divided by K. But when I checked to see if the lumped capacitance was valid, I evaluated a Biot number and I used H R naught divided by 3 over K. So you can easily be off by 3 or a third in a spherical problem, or 2 or a half in a cylindrical problem. Guess what? The slab, the plane wall is good. So that's good. This L is the half thickness in both of them. Did I help you a little bit? Avoid problems? Put a footnote. Look at this footnote and be cautious because of the cylinder or sphere, the definition of Biot number. Okay, this is going to that figure 5.6. Notice that again, this is the R naught, the outer radius of the cylinder or sphere. Again, that definition, cylinder or sphere. Be cautious there. Don't mess up. Okay. Here's a problem with the solution already worked out. I like that. We have a solid 3 centimeter diameter sphere. You know what? They changed it. The only thing really changed was they changed from copper to glass. What would we know about copper? Great thermal conductivity. Look at copper's value K. Look at the glass K. Low. Right? This is a big difference. 388 versus 1.4 on the K. Yeah, the rhos and the Cs are different too, but the big difference, thermal conductivity. Copper easily conducts. Glass does not. So it's heated in a furnace for a long time until it's 80 degrees C. Deja vu, same problem. Comes out, exposed to air. Same T infinity, same H. How long will it take for the center of the sphere to be cooled to 50 degrees C? Now the center is important. So let's say you check the Biot number and it's 0.268. That's not much less than 1. But let's say you went ahead anyway and you solved this problem using the lump capacitance. You would calculate a time to be 87 seconds. Now we're going to spend and do a lot of work, and we're going to come in with the final answer of 131 seconds. What's your tolerance for difference, you know? If you're just trying to get within, you know, the first significant digit, I know that this is, 100 seconds, and this would be 90 seconds. That's pretty close to each other. So I'm not discounting the lump capacitance. It's still going to get you close. Even if the Biot number, now if the Biot number came in, it'd be 2.268, you'd be further off. But 0.268 is closer to being negligible than 2. All right, so now what do? Is you want to use the whole series solution technique. You calculate the theta hat or theta asterisk. At the center line is going to be 0.5. You assume that the Fourier number is greater than 0.2 to use only the first term. And you calculate the Biot number. Notice when I use that table, I only use R, not L sub C, which is difference by a half. So, this for a sphere, it's difference by 3. Notice, take this number, multiply by 3, and do you get 0.8036? Yeah. And now you use that, go into the table to get zeta 1 and C1 for spherical, third column over. And you can now calculate the Fourier number. Just solving for this equation for Fourier number comes in around 0.4. I expected it to be greater than the 0.2. It looks good. Then unravel the Fourier number to get the time. Fourier number R squared over alpha. There you go. Not only can you get the temperature, but you can get the total energy transfer out of the slab or out of the cylinder. So think of Q naught. So you have rho CV times T initial minus T infinity. That's the maximum amount of energy that can be transferred out. If you knew the temperature distribution at an instant in time, compare it to the initial uniform temperature, then you get integrating over the volume, you can get what is the Q that comes out. And so for Fourier number greater than 0.2, you get a simple solution. Oh yeah, what does those 3 red dots mean right here? Lots of work, but it's the math class for this class. You find that you can get the Q over Q naught 1 minus zeta, sine of zeta 1 divided by zeta 1 times the theta asterisk at the center line or midplane. Now you do the same thing. Once you've done it for a slab, you can do it for a cylinder or sphere. Oh boy, professor, what is this? J1. Bessel function. can your calculators handle Bessel functions? I'm not certain. I think mine can, but in the interest of time, we'll skip it. Now, for a sphere, you have the same thing. So here, no Bessel functions. There you go. Those are the equations 554 of 555. Let's solve this problem. Plain wall of 50 millimeter thickness. Initially uniform temperature at 0 degrees C is well insulated on one face. Well insulated on one face. So if it's well insulated and its thickness, so it's going to go 0 to L like that. L is 50 millimeters. Okay. Suddenly exposed to a hot fluid. So we're going to be convecting with an H of 500 watts per meter squared degree C and a temperature of 60 degrees C, and the T initial was 0 degrees C. It's going to be heated. We have a hot fluid. It's turned it around, but the math is still good. The math works itself out if it's being heated or cooled. No problem. The wall has a given density, rho, of 708.30 kilograms per meter cubed. Specific heat, 435 joules per kilogram degrees C, and a thermal conductivity of 63.9 watts per meter degree C. And so the alpha, if you K over rho C, 18.8 times 10 to the minus 6 meters squared per second. Okay, calculate the surface temperature at a time of 500 seconds. What's going to be the first thing you try and do? See if lumped capacitance is justified. So Biot number, is it H, L divided by K, or LC? In this case, what is my length? Should I use half of 50 millimeter or 50 millimeter or 2 times 50 millimeter? So L, should I use 25 millimeter, 50 millimeter, or 100 millimeter? Answer A, B, C. Oh, we'll put in D. I don't know. And we'll show the results. And it is just simply 50 millimeter. The insulated is just like having the other side of going to negative L to 0, and then it also having the same convection on that side. The insulated is just like the other previous cases we've studied. Okay, now you calculate this Biot number. It comes in at 0.394. What should you do? Well, if you use the lump capacitance, it'll get you in the ballpark. At this point, I recommend you use the lump capacitance just to see roughly what we're talking about. But I would then come back and bulldoze through the math with the detailed solution and then know that they'll be comparable. Maybe not agreeing that well, but they'll be in the vicinity. Okay, so calculate the surface temperature at that time. So what is, just using lumped capacitance, what do you have? Theta asterisk is equal to e to the minus t over a tau. What is my time constant for this problem? Well, no, just the time constant. Just the mass specific heat divided by HA. All right. So if I do the rho C, the L times the A divided by HA, the A's cancel because of slab. And so now I'm ready to substitute numbers. Rho is 7830. Specific heat, 435. L is 0.050. And H was 500. So 0.605. Okay, 05 seconds. Okay. At a time of 500 seconds, so theta asterisk is equal to e to the minus 500 divided by 340.605. 0.23. Anything else? Oh, good. 0.23. 0. All right. So now this theta asterisk is the temperature minus T infinity divided by the initial temperature minus T infinity is equal to 0.23. So calculate the surface temperature at 500 seconds. Temperature is equal to T infinity plus T initial minus T infinity times 0.23. So let's substitute our numbers. Our lumped capacitance approximation would give us T infinity of 60 plus initial is 0 minus 60 times 0.23. What do you get? $46.6. 46.2 degrees C. Okay? Now, that's lumped capacitance. If you're interested in the surface temperature 500 degrees C, I'd expect it to be in that vicinity. I'd expect it to be a little hotter, but we just calculated it to be, the more exact I have coming in at 45.7 degrees C. That's actually, the lumped capacitance is pretty good. But the average temperature is lower. No, it's higher. I don't understand. I'd have to look at it some more. I would expect this number right here in red, when we use the more exact, to be a little hotter. But that's okay. Let's press forward. Let's use now the full solution. So basically, you have to calculate we already got the Biot number, right? The Biot number was 0.394. We need to get zeta 1 and C1 out of the table. So you get the zeta 1 and C1. The C1 comes 1.0573 and 0.5891. Okay.
Exactly, so we'd have to interpolate.
Yes, you'd have to interpolate.
But on the test, would you want us to...
Theta asterisk is equal to C1, the cosine of zeta 1 times x asterisk, which is going to be 1 if you're looking for the surface temperature. And then you have exponential of minus zeta 1 squared Fourier number. So the only unknown is the Fourier number you have to compute, right? The Fourier number is alpha t divided by L squared. We had the 500 seconds. The Fourier number comes in at 3.76, and I probably should have kept more digits on that. Because this is the value of alpha. We have it right here. Maybe I should have kept more digits on that alpha. I don't remember if I kept all these digits. But I should keep more than 3 significant digits on all intermediate calculations. This is truncated to 3. Okay. All right. Then I put in zeta 1 squared, exponentiate. This is 1, zeta 1, cosine. Put in C1, and then you get that this theta asterisk comes in at 1.0573 cosine 0.5891. Hey, professor, should I leave mine in degree mode in my calculator or radian mode in my calculator? It's not going to matter, will it? No, you learned that in statics. It does matter. What are the units on this zeta in the header of the table? Radian. Put it in radian mode. Thank you. Okay, exponential minus 0.5891, all of that squared times 3.76. And let's see what we get for a number. 0.24. No other digits?
3, 4.
3. Next one?
4.
4. Let me see if I get a couple agrees. I need it to 4 digits, right? 0.2434. Initial, which is times the 0.2434. So this is negative 60 times 0.2434. And that theta was the temperature minus T infinity. So if we do this, we'll put T is equal to T infinity, which is 60. Then we put minus 60 times 0.2434. And so what do we get for the temperature? 45.4? All right. Well, I had it at 45.7 in my other calculations. So very close. Well, with that, I thank you for your attention. Next time, we move into semi-infinite solids. Thank you.